Okay. Okay. So let me start off. Thanks, Lieven, for the introduction. So quickly about us. There's a third guy in our team, actually, Martin, but he has to give another talk actually with you, Lieven, I guess, and still has to prepare, so he can't talk today. You can also find us at kittenpics.org if you want to have some updates on what we do. About this talk, we are actually today going to talk about a practical evaluation of client-side XSS filtering. First and foremost, the XSS auditor that is built into Google Chrome. And in our work, we found a couple of bypasses that allow us for certain situations to bypass its protection capabilities. And basically, based on these observations that we made there, we kind of came up with a new means of protecting against specific client-side XSS vulnerabilities. So we're not trying to target server-side XSS, but purely client-side XSS vulnerabilities. I do have to run through those slides really quick. I hope you will bear with me, even most of you will probably know what XSS is. Before we start talking about XSS, let's briefly talk about the same origin policy. So a question is, why can't a domain, say attacker.org, read the emails that the visitor has on Gmail? Right? You can just open an iframe and read the emails, right? No, actually you can't, because there's the same origin policy in the way, which basically defines application boundaries by an origin, and the origin is the protocol, the domain, or the host in terms of an IP address, and the port. And the attacker's code just simply runs in a different origin, so you can't actually access it across these boundaries. How can we actually bypass the same origin policy? There are a couple of ways of kind of doing that on purpose if the developer really wants to do it. But more so, obviously, XSS is a problem. So applications typically have some form of user-provided data, right? Because otherwise, if you don't have data in your application, it doesn't really make sense to have an application. And this data may be stored on the server side or in the server, or it might also be reflected back. Think of, for example, a search field where you see, hey, you search for X, Y, and Z. And if we look at this piece of data here, presented as work, right? If this piece of data here, so this script alert 1, this is actually data that is being input into the application, but if it comes back in that exact way to the client, it's actually interpreted as code, because obviously it's JavaScript code. And it's executed in the origin of the vulnerable application, therefore we have cross-site scripting, so attacker.org is capable of then kind of retrieving the secret emails from gmail.com. So what can an attacker do with an XSS vulnerability? They can open an alert box. Wow. Oh my goodness. Obviously, this is what you do if you want to have a proof of concept, and this is also what Sebastian is going to do today. But rather, this means you can execute arbitrary JavaScript. Typically, things you do is you try to hijack a session. So for example, steal session cookies if they are not set to HTTP only. You can kind of control the victim's browser in any way you actually wanted to. So you can, whatever, for example, post something on Twitter about this crappy talk you're seeing right now. You may alter content. There's a famous example of the German Chancellor's website from a couple of years ago where somebody found an XSS and they used it to post some news about her resigning and for some greater good or something. And also something that people are typically not really aware of is some work we did for Black Hat Europe here actually, exactly in this room last year. Basically, you can actually steal passwords from a user's password manager. Basically, what you can do is you can do everything with the web application that the user can do. There are different types of XSS, and we kind of, see two dimensions here. So we see the server side and the client side. This is the one dimension, and the reflected cross-site scripting and stored cross-site scripting. Today, we're only going to focus on the lower half here. So we're only focusing on client-side XSS, not on server-side XSS. So what is DOM-based or client-side cross-site scripting? This is basically a term that subsumes all classes or all vulnerabilities that are purely caused by flaws in client-side code. So we have data from an attacker-controllable source. Think about, for example, the URL. That is something an attacker can control if they open an iframe, for example. And that ends up in a sink, which is basically the same thing as on the server side as well. Only difference is there are different sinks on the server side and on the client side. So in this case, for example, document writers, you can see up here, this constitutes a cross-site scripting vulnerability. And how do you actually detect these kinds of XSS flaws? You can do dynamic analysis. For example, Dominator does that. Also, we kind of wrote our own tool for Chrome using taint tracking, so basically tracking the flow of data from this source to a sink, and then seeing, hey, there is something fishy going on that we can exploit. You might also do static analysis, but please don't ask me about static analysis. We have no specific knowledge of that field of research. And in order to stop XSS attacks, you can do several things. If you're the application's owner, you can, for example, you can kind of best practices to not use user-provided data in an unsecure manner, right? This is very obvious. You can use some secure frameworks. I think in most modern web application frameworks, you actually need to opt out of these automatic encoding kind of functionalities rather than having to specifically filter or encode anything. You can use content security policy, sandbox iframes, etc., etc. If, however, you are not the application's owner, but rather you're the application's user, there are also something that you can do as the user. You can, for example, turn off JavaScript. I wouldn't, really try to turn off JavaScript on a large number of web applications because they will most likely break, or you can use a client-side cross-site scripting filter. I think the first one was NoScript, which is for Firefox, which doesn't have one built in. Internet Explorer ships also a built-in XSS filter, and then there's Chrome, and this is also the kind of the main topic of our talk today, who kind of carries the so-called XSS auditor, which is actually part of Blink and WebKit, so also Safari carries it, all browsers that are based on this this rendering engine. Okay, so this talk today is about client-side XSS, and in order to discuss client-side XSS, we wanted to have some real examples. Thank you. Real-world client-side XSS, and we did some work with this Taint-aware Chrome engine that we built to find this at scale. And this is research from, I think, 2 years ago, but it's still basically ongoing. And how can we actually go ahead and finding these flaws at scale? So first of all, as I already mentioned, we have this Taint-aware browsing engine, the Chrome engine. This works on a byte level. That means for each character in a given string, we can specifically say where it came from. Was it hard-coded? Was it from the URL? Was it from the cookie, et cetera, et cetera? Based on this, or on top of this Chromium browser that we built a crawling extension that would actually obviously crawl a large number of websites, but also collect all these data flows that we discovered from attacker-controllable sources to these security-critical things, such as document write. On top of that, we built an automated exploit generator because if you, for example, if you know what the URL looks like, you know exactly in what context it's being used, you know how to manipulate the URL such that you can actually introduce your own JavaScript code, and Sebastian will show you that in a couple of minutes. And final step, just because we saw a flow of data from a source to a sink, and we think that we are capable of controlling it completely, it doesn't really mean that we are actually able to control it. There might be some filtering involved. For example, there might be quotes might be filtered, or opening and closing brackets might be filtered. So what we need to do in the last step, in the final step, is to verify that these exploits actually are in existence. This is basically done again by, after having generated these exploit URLs that we want to test for, we feed them back to our Chrome crawling engine, and basically it opens up a lot of alert boxes. And we ran this experiment on the Alexa top 10,000 domains. We went down, I think, 2 levels from the start page, so not really kind of deep into the web application. We didn't try to log in or anything. We didn't interact with the website at all. Just basically load the website, do not click anything, just record all the flows. And in total, we found over 1,600 unique vulnerabilities spread across 958 domains, so roughly 10% of all of our kind of domains in our test set contained at least one of these XSS vulnerabilities. And we disabled the auditor during compile time. This is due to the fact that just because this kind of last means of, or this last line of defense protects us, does not constitute that there is not actually a vulnerability, right? Because there is still a vulnerability, it was just caught by the auditor doing its job. And so after this initial kind of discovery of this data set, we went ahead and said, hey, let's rerun this experiment and turn on the XSS auditor. And without actually trying anything, like trying to evade it or something, we found that it did not catch all of the exploits. So we were wondering, okay, so why is that exactly? Is there some reason for that somewhere in the code? So we conducted kind of an in-depth analysis into the why this actually happened. And this is where Sebastian will now jump in. And we now have to switch kind of the microphone.
Sorry. Sorry, we only had one microphone, so we had to switch. Okay, so as Ben said, I would now like to talk about the XSS auditor and explain a little bit how it works and how we managed to bypass it in a lot of different cases. But before doing so, I would like to explain like the basic, how it works, how it does its magic. And what the XSS auditor tries to protect against is the reflected DOM-based, the reflected cross-site scripting attacker model. So in this attacker model, we have an attacker, and the attacker wants to craft an attack. So he crafts a URL which contains markup, HTML or JavaScript, and the attacker sends this URL to the user. And the user, well, clicks on the link and opens it in his browser. And what is happening is that in the reflected case, the payload that the attacker inserted into the page somehow shows up in the HTML code of the page. And you can see it here. So we have a script tag. So this payload executes, and here it's an alert box. And this is exactly the situation the auditor is looking for. So it tries to find, while parsing the HTML document, find these potentially malicious constructs, and it then tries to find this in the request. So in this case, the payload is contained within the URL, and if the auditor is able to find this and make a connection between those situations, it will flag this as an attack, and it will just remove the script tag from the page to make the page work, but to prevent the attack from happening. And the main assumption that the auditor does is that an attacker always injects HTML code to execute JavaScript. So for example, the attacker uses a script tag, as we've just seen in the example, or he uses an error handler, an event handler such as onload or onClick to execute arbitrary JavaScript. And the idea of the auditor is basically to prevent malicious HTML constructs from invoking the JavaScript engine. So this means a malicious HTML construct is something that was injected, so was contained in the request that was sent to the web application. And this basically explains the placement in the browser of the XSS auditor. So the XSS auditor is placed in between the rendering engine and the JavaScript engine. Or more specifically, it is placed inside the HTML parser, which is part of the rendering engine. So what the browser does, it parses the document, and for every node it finds, it checks whether this could be a construct that might trigger the JavaScript engine. And in case if this is the case, it passes the node onto the XSS auditor, and the XSS auditor tries to find whether this might be injected. And if it can find the thing in the request, it will say, this is injected. I block this transition from the rendering engine to the JavaScript engine. And in this case, the XSS would be prevented. So basically, there are 3 different ways of invoking the JavaScript engine from HTML. And well, the first way is pretty obvious. It's a script tag. So whenever the HTML parser encounters a script tag, it will execute JavaScript. The second way are dangerous HTML attributes. So for example, you can use an event handler, so something like onload or onClick, and put arbitrary JavaScript into there. Or you can use attributes that contain JavaScript URLs. So here, for example, we see an iframe with the source attribute, and the source attribute takes URLs, and you can just use a JavaScript URL. And the third way is referencing external content. So you can just have a script include from another page, or you can embed a Flash file, which in turn is again able to execute JavaScript via an API, or you can embed anything else, Java applets, Silverlight applets, and so on and so forth. And for all of these 3 situations, the auditor has one way of detecting whether something got injected. And what I would like to do now is to explain those 3 ways for these 3 different situations. So let's first talk about inline scripts. So whenever the parser finds an inline script in the HTML document, it first checks whether the tag name was injected. So basically, it extracts this tag name, and then it just checks whether the request, whether the post parameters or the get parameters somehow contain this string. If this is not the case, it will just let it through. If it finds this, it will also check for the content of the script. So what it does a normalization. So it removes leading comments and white spaces. Then it takes up to 100 characters, up to the first comment character it sees. And then it will check for this string. And if it finds both of these strings, it will block the attack. The second matching rule is for attributes. So whenever the HTML parser encounters an attribute, it does basically two checks. It checks whether the attribute contains a JavaScript URL, so basically if the string or the value starts with JavaScript colon, or whether the attribute is an event handler. This means it starts with the letters ON and has at least 5 characters. If it finds such an attribute, it matches the complete attribute. So it starts at the attribute name and extracts it until the last quote and will then match this against the response. And if it finds it again, it will block the request. And then there is a cert matching rule for external content. And whenever the parser encounters an external tag, it will again check whether the tag name is contained in the request. And if it finds the tag name, it will also check the attribute that references the external URL. And when it finds those two strings, it will block the request again. So to summarize this is how the auditor works. So in the beginning, we have an invocation phase. In this phase, the rendering engine decides whether to give something to the XSS auditor, whether this might be a malicious HTML construct. After that, if the XSS auditor is invoked, the XSS auditor does a matching. So he extracts those different parts that I just showed and checks whether the URL or the post parameters contain this string. And if it finds the string, it will block the request. Otherwise, it will leave it through. OK, so now let's talk about how to bypass this thing. So basically, we have two different possibilities here. So we can either prevent the XSS auditor from being invoked, or we can stop or confuse the matching. And if we can somehow make the XSS auditor not find our string in the request, although it's there, we can avoid blocking. So let's first talk about the invocation thing, and later I will have some examples for the string matching issues. So basically, there are 3 different possibilities how you can prevent the XSS auditor from being invoked. And the first reason is, and this is somehow a misconception of the auditor, the idea of the auditor is that an attacker always has to execute HTML to execute JavaScript. And this is a mistake because there are XSS vulnerabilities where you don't need HTML at all. For example, you can have functions such as evals, a timeout function, where you evaluate code with it. And these functions are residing in the JavaScript engine, and they can directly from the JavaScript engine read user input. So there's no need for HTML parsing in this case. So you will bypass the auditor. And another thing is also the DOM bindings. So instead of like writing raw HTML, you can just construct in JavaScript an element and then just assign to its attributes things without HTML parsing going on. The second reason why the auditor might not be invoked is performance. So we encountered a lot of situations where protection capabilities were switched off because we found some bugs in the public bug tracker where they just said, oh, we deactivated this caused performance issues. For example, one thing that caused big performance issues is parsing of document fragments. So whenever you invoke things like inner HTML, outer HTML, insert adjacent HTML, they had a lot of performance regressions, so they just switched off the auditor for these APIs. And then there's also another performance optimization, and it's for unquoted attributes. So what the auditor does before being activated, it checks whether the request contains one of those 4 characters. So opening and closing angle brackets or quotes. If your request doesn't contain quotes or angle brackets, the auditor will be disabled, and you can do whatever you want as an attacker. And there are some XSS attacks where you can do an attack without these 4 characters. And the last situation, how we can avoid the invocation, is that sometimes the malicious code does not need to be in the request. For example, with HTML5, we have some new nice APIs. We have, for example, post messages. We have WebSockets. We have WebRTC data channels. So we have different ways of getting data into an application besides the requests. If we can use them, we can circumvent the auditor. Also, if we can temporarily store payloads somewhere, for example, in local storage or in cookies, then we can, because it only compares the immediate request and response and not the request that happened before. So if you can like store something in the first request and then send a second request to receive it and execute it, the auditor will not find this. Okay, so these are the invocation things. Let's now talk about the string matching issues. And I will present these as demos. So I will now switch to our taint engine. So basically, I need to change the settings. Otherwise, it will look pretty ugly. Okay, it takes a while. Yes, there it is. So here I have two things. So I have our taint engine, which gives us some information on the data flow, and I have Chrome Canary. So the newest version of Chrome, so we can check that the bypasses actually work in the newest version, because most of them are design issues and cannot be fixed. So let's first see. We have 3 examples. This is the first one. And basically we identified, so what we did, we read the source code of the XSS auditor, and we identified in total 17 different bypasses. And for these string matching issues, we have 3 different categories. And for each category, we have only one example, because we don't have the time to show all of the examples. So the first category that we will show is called partial injections. These are injections where we have some surroundings happening. And in our taint engine, we can actually see what is happening. So we have a URL, and we have some value in the fragment. And we see that here is a document write happening. And we see the code, the actual code that was document writed. And we see the value that was tainted, that was coming from user controllable value. So we can change this, and we will see it will change here as well. So how would we exploit this? So in the usual case, we would exploit this by breaking out of this attribute. Then we would close this script tag here. So we'd just add a closing script tag. Then we would open a new script tag, would write alert1, and close the script tag as well. So this should execute. And in this browser, we have the XSS auditor switched off. So I will now switch to Canary to show that it's actually blocking the thing. So you don't see an alert window. And if we check the console, we see that there is an error message saying that the auditor found an attack and it blocked the attack. So the interesting thing here is that actually we are not injecting in a green field, but there's some surroundings. So we are already in a script tag. So basically there's no need to close the script tag and open a new script tag. So we can just use the script tag that is already there. So instead of closing and opening, I just remove this and this variable declaration here. And then I just enter alert and close the script tag here. If I do this, we see the alert, but here the auditor is not activated. So let's copy this to the Canary version. And we also see the exploit, the alert box here. So we just bypass the XSS auditor in this case. And for this category of partial injections, we have 4 different exploits or exploiting situations that we can exploit. Okay, so let's have a look at the second example. The second example is, we call it trailing content. It's very similar to partial injections, but a bit different. So what we see here is we have, again, a value in the URL, and we have a document write, and we write div tag, and the injection is inside an attribute. And what we see here is that after the injection, we have some characters. So we have the value from the user, and we have these characters. So usually, how we would exploit this, we would break out of the attribute, we would close the tag, then we would open a script tag and so on, or an iframe with an event handler, and this will also be blocked. And the interesting thing here is we can make use of the trailing content to confuse the XSS auditor's matching rules. So if we remember, if it finds an attribute, it will match the complete attribute against the request, and it tries to find the complete attribute. And what we can do is we can use this PX here. So for example, I can just use an iframe, and then I will just request some arbitrary thing that doesn't exist. And then I will use the onload event handler. And so instead of closing this, I can just leave this onload attribute open. Because now this will be inserted here. I can just, what is this noise? I can just show this, so this alerts. And what we see here is that we form a new iframe tag, and basically the onload attribute is now not onload alert 1, but onload alert 1, semicolon px. And actually, this is valid JavaScript. This is syntactically correct JavaScript. It will throw a runtime error when it encounters the PX, and this is an identifier that is not defined, but actually only after our alert box is executed. So I can just show this in the Canary version. We see the alert box. Because now it's trying to matching the whole attribute, but the whole attribute, the PX is not contained in the quest, so it's never able to find it. Okay, and then we have, so for this trailing content category, we also have 3 different exploits. And basically for this to happen, the trailing content somehow needs to be syntactically correct JavaScript. In this case, so this is the naive attack. We have a much more complex attack where we can also have arbitrary trailing content that is not valid JavaScript. So this works in most of the cases, only for a few characters. There are a few characters, such as quote. If the first character of the trailing content is a quote or question mark, then the attack does not work because the auditor has some logic built in. But it works in most of the cases. Okay, and then we have a third category, and the third category we call multi-injections. And usually, the auditor assumes that an attack always happens within one parameter or within one injection point. But actually, in our study, we found out that usually for every sync access, so for example, for document write or eval, you have on average 3.8 injection points in one string. So actually, you can make use of this. So let's have a look at this example. So what this does is we have a document write, and this document write writes an image, and we actually have 2 tainted values coming from the URL. So we control both of them. So what we can do, so usually what the XSS auditor assumes an attacker to do is to break out of the attribute, then close it, and put this whole payload into one parameter. But actually, we can split the payload. So what I will do now is I will break out of this first attribute. We'll just close this image tag, and then open a script tag. And if I open a script tag now, this is the following content that follows the script tag. So I somehow need to make sense of this. So what I just do in the script tag, I just open the void function, which does nothing, and start a string. And now I use the second character, the second injection point. And for the second injection point, I just finish the string, close the void function, and then just use my payload alert1 and put the script into there. And we will see the alert is, but the XSS auditor is off now. But what we see is that actually we have 2 tainted inputs, and the tainted input is here, and the tainted input is here. And if you remember the matching rules for scripts, we know that it first checks whether the opening script tag is found, and it finds it, because we have an opening script tag in the URL. But then it uses the first 100 character of the script until the first comment. So it just matches the whole content of the script. So it tries to find this in the URL. And if we watch closely, we don't have strings in between. So the matching fails, and we have bypassed the auditor. So we try this in Canary, and we see the alert. It works. So for this category, we have 3 different exploits, and it also works if you only have one value that is echoed twice in the page. That also works. Okay, so let's switch back to the presentation to hurry a bit. So we saw demos. So what we did is we had 17 different exploits for the XSS auditor. And we had this taint tracking engine, which is automatically capable of generating exploits and finding vulnerabilities. So what we did is we adapted our exploit generator to generate bypasses. So it's automatically capable of generating those bypasses, and we then just evaluated how often are these situations present that we found, and how often can we exploit. So we had 1,600 vulnerabilities, and in these 1,600 vulnerabilities, we were able to bypass the auditor in 72% of all the cases, and actually in 80% of all the vulnerable web applications. So some applications had multiple vulnerabilities, so we were able to exploit most of them. Only the simple injections were caught by the auditor. Some issues have been fixed, 2 or 3 of them, but most of the things are design issues. Okay, so now we will switch back to Ben again. and he will talk about our solution to that problem.
Okay, so we got a second microphone now. That's awesome. Yeah, so doing it the right way. So now that we've seen what Sebastian just told us, we see that the auditor actually has several problems. So problem number one is that it uses kind of an approximation of a string matching. Give me that mic. Sorry. It's easier. So we might have sorry for that. Can you hear me with that? I hope so. Okay. So we have problem number one is basically the approximation of a data flow. That means they try to use string matching to see, hey, there was a flow of data. Obviously, this is the only thing you can do on the server side because you don't actually have kind of taint tracking on there. Second problem was the location, right? It was situated in the HTML parser, and XSS is a JavaScript execution problem. It's not HTML code injection. And thirdly, and that's, to be fair to the guys at Google who did this, it was never designed to tackle client-side XSS, but rather server-side XSS vulnerability. So let's just try and fix that, right? So we propose the following solution. This approximation of a string of a data flow is unnecessarily imprecise for local flows. We can just use taint tracking, right? We saw that just now. We should also position kind of our solution inside the JavaScript parser because cross-site scripting is JavaScript execution or injection and not HTML. And XSS basically is something that I said earlier. It's data being interpreted as code. But what we want to do is we want user-provided data to always be interpreted as data, right? Nothing else. So in JavaScript, data is basically literals. And for our case, we say we only allow kind of tainted data to generate string literals, numeric literals, or Boolean literals, and nothing else. Let me briefly show you an example here. So we have a vulnerability up here. So we have some user input up there that goes into eval. And actually, this is if we kind of provided like the string user data, this is what actually ends up being, it's not working, awesome. This is what ends up being passed to the JavaScript engine, right? So if we kind of look at the kind of simplified abstract syntax tree here, we have a declaration with an identifier. We have some tainted value, which is denoted in red here, user data, and we're fine with that, right? So that's okay. In the case, however, where we try to actively exploit the whole thing, our code that is being passed to eval looks more like this you can see up there on the right. So what we see now is that the syntax tree looks somewhat different. And remember our policy, we just stated that we only want literal values to be tainted. What we do see here is we have a tainted identifier, namely alert, and we have a tainted literal down there, 1, which is okay, but still this alert is tainted, violates our policy, so we're not happy about that, and we're actually gonna block this. So block policies, just mentioned that, tainted values in terms of the JavaScript engine. Sebastian also said that, there are different ways of injecting kind of your content. You can also, for example, reference external content, right? You can write script source, attacker.org, and include your own JavaScript. So no element that references external content may have a tainted origin. Yeah? Remember the origin, I talked about this earlier. This is enforced in the HTML parser and in the DOM bindings. There's one single exception to that rule. If it's the same origin as the page that is kind of including it, we allow it. Because obviously, if the attacker was able to kind of control that domain, he wouldn't need XSS to begin with, right? Okay, so now that we have this solution, we evaluated it in kind of 3 different dimensions. First of all, false negatives. So we ran it against this set of kind of the known vulnerabilities that we had. And, well, it caught all exploits. This is not really that big of a surprise because it was our test set to kind of check the soundness of our engine. And obviously, the issue here is that we don't have a ground truth. We don't have kind of all client-side XSS on the web. I think we have a fraction. But I guess I think the concept is sound, and if there are things that allow an attacker to bypass our protection capabilities, it's basically an implementation issue that should be relatively easy to fix. More interesting are false positives in this case. So what we did a compatibility crawl of the Alexa Top 10K, crawling about 9 million frames, or in roughly 1 million URLs. And we found that we caused issues on a total of roughly 15,000 different documents. So 0.016% false positives. This sounds acceptable. And these were actually instances of kind of people using user-provided input to generate code, which is not necessarily a good idea. If we look, however, at the domains, we see that these are kind of spread across 183 domains. So we kind of interfered with some functionality. I think it was always just one functionality on any given page of these pages. More interestingly, we actually see that, that half of those are actually exploitable domains. So this is basically XSS by design, where people just, well, they have like evil.html, which gets some user-provided string and just executes it. Great idea. Then we evaluated this kind of in a third dimension, namely the performance. These are the results from kind of evaluating with 4 different well-known benchmarks. We basically took our Chrome. We took a baseline version of Chrome, so an untainted version. We took Firefox and Internet Explorer. And as you can see here, there's a patched Chrome worst and a patched Chrome. If you think about tests that try to evaluate the performance of a JavaScript engine, those tests will not necessarily use tainted strings, right? They won't kind of write something to the URL and then use it again. However, our taint checking kind of see whether something is actually kind of injected by an attacker only needs to kind of be taken care of in cases where there is a string that is actually being tainted. So for the patch Chrome worst, we just kind of assumed that all strings were being tainted to kind of get a kind of a maximum upper bound of over the overhead. And what we do see here is that on average, basically, if we look at all the tests, we obviously perform worse than Chrome. We do outperform Firefox still. We do outperform Internet Explorer in all cases but SunSpider. But there's kind of a, well, let's call it optimization in Internet Explorer that detects kind of so SunSpider makes use of a dead code loop, basically, to, I don't know, it's executed, I don't know, 100,000 times. And IE has a dead code detection, or so they say. There are some tongues on the internet that say they are just detecting this specific version of the SunSpider benchmark and just skip that part and not execute it. Okay, conclusion. We found XSS or client-side XSS on at least 10% of the Alexa top 10K domains. We actually still have that same number, just run it in an experiment a couple of weeks ago. We conducted a security analysis on the state-of-the-art of cross-site scripting filtering, namely the XSS auditor. We did found several bypasses, both in the invocation, as Sebastian discussed, as well as the string matching that was being used. And basically, looking at kind of the issues that were the root cause of these problems, we derived a new way of filtering against client-side XSS. So we proposed this new approach using exact taint information that we had patched into Chrome already anyways. We had no false negatives with respect to our data set. We had pretty low false positives. And even so, if there was a false positive, it was just one minor component on a website, so it wasn't like the website didn't work anymore. There is some overhead, which we believe is improvable, but again, it was kind of a proof of concept research prototype that we built and not a ready to release Chrome version. And yes, thank you. With that, I'd like to thank you very much for your attention and be happy to answer any questions you might have. That's a good question that we get asked quite regularly. So the initial version that we did this with Chrome is like 36 or something. I did talk with Ulfa Ellingsen from Google last year, and it was interesting. So he asked me the exact same question and said, hey, you should open source it and mainline that. And then he said, yeah, but the Chrome developers would never allow that in because they don't know me, and it's kind of a massive change to the whole infrastructure. If ever I had like 2 months of time, I would really like to do that, but it's a good question whether I will actually have the time at some point.
So I think one big problem here is performance. So in the best case, we have like 8% performance overhead. The worst case, I think we have 16, which is way over the top as what Chrome people would accept. So I think 0.01% would be too much for them. So basically, I think they are not interested in that performance hit for just one security feature. So I think the performance of our thing is improvable because we are not like, we didn't spend a lot of time in optimizing all the things in there. We just patched in the functionality. So, but I think the performance is a big problem. Okay. Thank you very much.